Vector fields can be a way to represent what the gradient means. So let's look at the surface z equals x squared plus y squared. And I actually like to think about this in polar or cylindrical coordinates. This is the surface z equals r squared. That helps convince me that this is a paraboloid. Because then, if I just go to, let's see, r equals 0 would have given me z equals 0, r equals 1 gives me z equals 1, r equals 2 gives me z equals 4, and so I end up with this like parabola looking shape, but it's rotated all the way around. Maybe draw that better. Nope, that's not better. Okay, well, there we go. Be a little more careful, you can get a better sketch. Okay, so there's that paraboloid, and then let's calculate the gradient, del of z. So I take the partial derivative with respect to x, which is 2x. Partial derivative with respect to y is 2y. And then what does that mean in general? Well, this means at any point, x comma y, in the whole plane, we get a vector. Right, at any point, and then you can be on the surface or not, but there is some vector that tells you how far up we're going if we walk in the x direction, and how far up we're going if we walk in the y direction. So let's go down to the xy plane so we can sketch this. Let's see what happens. At 0, 0, we get the vector 0, 0. At 1, 0, we get the vector 2, 0. And then at 2, 0, like, these vectors get bigger. And it turns out, like, at 1, 1, we get the vector 2, 2. And it turns out these vectors get bigger. So any direction you go in, the vectors are getting bigger the farther out we go. Maybe that's not as big. And so, let's see, here we get the vector 0, 2, but over here it's bigger. And then pretty soon we can get something called a vector field, or in some other courses you may have seen it called a slope field. So in Math 307 these are used. And these are good for going backwards. If you have some information about derivatives, can we recover the original function? That's called differential equations. So a lot of uses for these, but currently this is like an arrow diagram that physically represents what the gradient is. And what this diagram does is it indicates which way is up and how far up. So for example, if I did walk to the point 1, 1, I'd be here on this graph, and then this way is up, and it's up by that much, a medium-sized arrow. And then if I walked further out to like maybe the point 3, 3, then I have a much bigger arrow because the surface is now steeper by the time we got to that point, and so on. And another way of thinking about this is if I somehow reverse the direction of all the arrows, so now I have something like that. They're all pointing to the center, and then I have bigger ones pointing to the center out here. Reversing the direction tells you which way you would slide. Reverse direction of all arrows tells you which way you would slide or fall. So I'm really into water slides. If you had an interesting looking water slide, so not really a water slide, but a circle. It's actually a ride like this. I don't know if any of you have ever been to Wildways down in Federal Way, but they do have like a circular thing that you can go down. And then if water wasn't moving, if you were just letting it fall and you sat there, you would slide down that way. And then this reverse diagram arrow tells you that, with that arrow to the center.